Hello, this is Anurag. Uh, Welcome you all to a new series which is on microwave and millimeter wave circuit design. Now I'm going to use different tools for this, so I'm not saying it is using ADS or EM Pro or HFSS or other tools. I'm just saying microwave and millimeter wave circuit designs. Now here uh, in this series we are not only going to discuss about the passives but also the active circuits, right? So unlike some courses which are just passives, right, and some courses just focusing on antenna, or some courses focusing on just the amplifiers and things like that. Unlike that, this course is basically a more comprehensive course where I'm going to cover everything from a something on a laminate, or let's say LTCC process, right, passives on that, to something like packaging, to something like antenna designs or array designs, to something like IC designs, whether it's a gallium arsenide or it's a gallium nitride, or even if it is a silicon RF CMOS, right? So I'm going to discuss that. Now, first thing first, in microwave and millimeter wave, we are talking about some form of a wireless communication or a radar application where the medium is free space, right? So there we are talking about propagation in the medium. We are also talking about propagation inside the circuits along certain lines or transmission lines, right? So the propagation in the medium is referred to as what you call free space waves, while the propagation of EM waves along a guided path or a trace, that would be called guided wave, right? So we are going to discuss these two, and we are going to discuss various circuits which are passive circuits, also some circuits which are involving some form of magnetics, like for example circulators and their designs, or let's say magic teas, stuff like that. So in this course, I'm going to keep it very generic, and I want to keep it the scope as wide as I can, rather than making separate small courses on filter design or let's say antenna design and stuff like that. I assume that everything is one. So I'm going to cover, there will be lots of sessions in it. So but to first of all, to get started in this session, I will give you a little bit of introduction on microwave and millimeter wave. So to start with, all of them are some form of a electromagnetic wave, right? So what do you mean by electromagnetic waves? uh, okay, the propagation in a charge free medium, okay, takes place as time varying electric and magnetic fields. Now the time varying nature of electric field, as we will see when we discuss Maxwell's equation, time varying nature of one form of field leads to other form, right? So that's why the electric and magnetic fields are supporting each other without the presence of a source in a medium, and that's how the propagation takes place. So for EM wave to exist in a medium, you do not have anything required from a medium. The propagation basically is E supporting H and H supporting E. So that is called electromagnetic waves. And second thing is that the electric waves, let's say sinusoidal in nature for the simplicity, then magnetic waves also sinusoidal in nature. They basically are orthogonal to each other and orthogonal to direction of propagation. So these kind of waves are known as transverse electromagnetic waves, or TEM waves. So most of the free space propagation, without involving any reflectors, without involving any charges or any boundary, most of the propagation in free space is a transverse electromagnetic wave. That's the natural way of propagation. So what I'm showing over here is, in blue we have got E field, and then in green we have got H field. So E and H are perpendicular to each other or orthogonal to each other in, let's say, x y plane, right? And then in the z plane, or rather you can say y z plane, and x plane is the direction of propagation, as I have marked here, right? So now what is happening is, the way to imagine is, let's freeze it in time. So when you freeze it in time, what do you have at time t1? Okay, at time t1, what do I see? I see that various points in space, okay, are frozen in time, right? But then they have different amplitudes, right? So basically what you can see is that in different time at different steps along x-axis, you can see E magnitude, right? So E magnitude forms a sine wave. Similarly, the H magnitudes also forms a sine wave. Now, if you see the ratio of E to H at any point in space, that's going to be a constant, right? So that is called, so if you take E and then you take H and you were to take the ratio of the two, you are going to have what is called the wave impedance. Okay, so this is a free space impedance, right? So this is the characteristics of the medium, right? So we will derive this later on when we solve these equations, right? Okay, so what is happening is this E and H are perpendicular to each other, and the direction of propagation is perpendicular to the both. So now how do you find out the direction of propagation? Let's assume that E collapses into H, right? So if E collapses into H, this is like a circular motion, right? So if E collapses into H, think it in terms of a screw, right? Which basically you are tightening, right? So you are going from E to H, okay? And the direction in which that screw will move, right? So for example, if you turn it clockwise, right, from E to H, then it is going to move forward, right? So that's what you can assume here would be the direction of propagation, and the direction of propagation is usually what you call poynting vector, right? So Poynting, poynting vector x. Okay, so that gives the direction of propagation. So you would have E cross H will be equal to S. So don't worry about what is cross, okay? This is going to be some form of a vector product, right? So we will see the details. Now let's unfreeze it in time. So we were talking about T1. Let's say we look at the time T2. In T2, what happens is you will see that each sample has moved at a distance of delta x, in the sense that it hasn't moved, but rather now whatever oscillation we were seeing at, let's say, x1, now you are going to see at x1 plus delta x, right? So you are seeing the same thing as x1 plus x. So every sample, the oscillation you are the distance delta x, okay, now it is in the same state of, in the same phase of oscillation as it was delta x before, right? So this is how the waves are propagating, the E waves are propagating as well as the H waves are propagating in the same way, right? So this results in what is called the phase velocity. The velocity which with a constant phase point moves in a space is called phase velocity. Phase velocity. Okay, so this is the velocity with which a constant phase point moves in space. Okay, so having said that, you will see that this represents, for example, a phase, and this represents a phase. So now it has moved in, the constant phase point has moved in space, okay, with a certain in a certain time t2 minus t1. So in this time you have seen that the constant point phase has moved a distance of delta x, okay. So this would be called the phase velocity, right? So that's how the propagation takes place. Now if you see in time, you would see that if you consider one point x1, then the oscillation over time also would be a sine wave, right? And you will have E and H doing the same sine wave, right? So in time also they are going to look like a sine wave, right? So you can imagine this way: if I pick up any point in x, so if it is going to this amplitude up to here, now next time it will be going to an amplitude which is much bigger, and then next time much bigger, and then that way it will also be a sine wave, right? So if you discretize in space, you are going to see a sine wave propagating, but if you discretize in time, you will also see the samples moving in time, right? So you will have oscillations in time as well as oscillations are moving in space, right? So this is how the EM wave basically propagates. Now, this EM waves, okay, when we study this, any textbook restart would various bands of various frequencies are arranged in various bands, and these bands are allocated for various applications, right? So for example, if you go from 1 to 2 gigahertz, it will be L band, 2 to 4 it will be S band, 4 to 8 will be C band, 8 to 6 8 to 12 will be X band, 12 to 18 would be K band, Q band, and 18 to 22, let's say, is K band, 22 to 26 is, let's say, K band, 26 to 40 is U band, around 50 gigahertz, so 40 to 60 is around V band, then anything above 50 going up to, let's say, 100 gigahertz would be W band. So most of the people, they say, okay, we are going to design a circuit in a certain band, okay, but what is the basic difference in designing different bands? According to me, there is no difference. It's just a frequency is just a number. Only thing is that when you go higher in frequency, you have to be careful about some of the effects which were not so dominant at low frequency, right? For example, the ground is no longer a point, it's a distributed ground, right? So whenever you design something or cascade something, you always specify impedance with respect to a local ground instead of with respect to infinity, right? So that's why in most of the designs, when you simulate, you do not use single ports. You are going to use ground reference ports. So we will come to this when we design circuits and cascade them. Okay, so these are the various frequency bands. Now, what is the advantage of going up in frequency band? So what happens is, it is all a question of technology, right? When we started, we were working in low frequency bands because we didn't have devices and we didn't have that kind of a what you call a process where we can do very fine components and stuff like that, right? So we started with a low frequency band, but there are advantages associated going with a high frequency. First and foremost, or obvious advantage, so advantage of migrating up in frequency. Okay, advantage of migrating up in frequency. Okay, short form. Okay, so what are the advantages of migrating up in frequency? First advantage I see is that the bandwidth is usually a percentage of the center frequency or the carrier frequency. So if I say 10% bandwidth in 60 gigahertz, it's going to be 6 gigahertz. 10% bandwidth at 6 gigahertz would be around 600 megahertz, right? So you see that the bandwidth keeps on going up as you go higher frequency. So that means that the communication systems will have high throughput rates. High throughput rates, or data rates can be high, or we can make a broadband system where we can transmit much more information in that band. Okay, so going up in frequency, we can have higher bandwidth, means high throughput rates. Second and very obvious reason for going up in frequency is that there are 4 kinds of noises. Okay, ignoring all the interference noises, there are 4 kinds. Okay, so these 4 kinds of noises are flicker noise. So the flicker noise is usually in the active devices, flicker noise. Okay, and this has to do with whenever you have got a junction between dissimilar materials, for example metal and semiconductor, or let's say silicon dioxide and silicon. So these interfaces have got these defects, or basically the places where the carriers can get trapped, and then after a certain relaxation time they get released, right? So this causes, okay, a certain variation in this charge when a current is flowing, right? So this appears as a noise which is known as flicker noise. Now, for example, MOSFETs, right? In MOSFETs there is a silicon dioxide and then silicon interface, and most of the defects are are at the gate level when there is this interface, right? So if you make the transistors which have more gate area, then this noise will average out. So larger the device, lower the flicker noise. Okay, flicker noise is usually a 1 by f noise. It degrades with frequency. So if you got high up in frequency, this noise will disappear. Next thing is the short noise. Okay, so short noise is whenever there is a p-n junction, then the carriers which are crossing the p-n junction, right, they basically cross in bunches because they take different paths. So when they arrive, they do not arrive as a smooth flow of current, they rather come as burst of these charges, right? So the noise associated with this burst rather than a regular flow of carriers, this is known as short noise, right? So short noise you will see wherever there is a p-n junction. Now this short noise also has a corner frequency. So if you go beyond a certain frequency, this noise will also go away. Okay, so these two noises, they go away at high frequency. Okay, the next thing is the burst noise. Okay, so this burst noise is due to the heavy ions. Like for example, if you do a metal implant, okay, to increase the conductivity. For example, if you take a polysilicon, and the polysilicon on its own is very resistive, but if you do an ion implant on a polysilicon, it becomes a conductive poly. But the problem with that conductive poly is that there is a heavy metal ion. So this usually results in a noise which appears like a burst, and this is usually in kilohertz range, right? So it affects your audio systems, right? So if you have an audio system, you have this hissing noise which you see, or some kind of a noise which you see uh, whenever the whenever the voice basically dies down, you can hear that noise, okay, in a speaker system, right? So it's usually in the audio range. So this burst noise is also not there. Okay, and then the very last is the thermal noise. So this is the only noise which you are going to see. So this is the only noise which you are going to see in case of high frequency circuits. So that's one advantage of designing this at the circuits, communication circuits at high frequency, is that the noise is only going to be the thermal noise. And then there are interference noises which I'm not covering right now. Okay, so what is the third advantage of doing this? Okay, the third advantage of going up in frequency is that as in basically what you call radars, right, or imaging, right? So higher the frequency, okay, finer is your resolution, right? So you can image, okay, objects which are much smaller when you go up in frequency. So if you were to make radars at L band or S band, they will not have very good resolution. That's why for all the automotive stuff we have radars set around 24 gigahertz band or 77 gigahertz band, because we are talking about objects which are much smaller, right, or the targets which are much smaller. So to resolve those targets you need a high frequency. So that's another reason is high resolution in radars. High resolution in radars. Okay, fourth most obvious advantage is, or rather a disadvantage, this time I'm going to say a disadvantage, or it is also an advantage in some sense. The advantage is as you go up higher in frequency, okay, then the path loss basically keeps increasing. So that means that if you have an isotropic antenna, right, and you are using it for a low frequency, then the path loss is going to be less, while if you use for a high frequency, path loss is going to be more. Now how come this is an advantage? So for example, in mobile systems, right, you can reuse the frequency when you go from one cell to another cell. So frequency allocation, right, it can be reused in a mobile communication system, so that improves the subscriber capacity. Okay, so that's the advantage. The advantage is frequency reuse. Okay, so that's the advantage of going up in frequency. Other than that, I don't see a lot of advantages. It's only that the designing becomes more involved. That's the only thing which happens for a designer. Other than that, nothing is special. Okay, so what are the various applications of these microwaves and millimeter waves? Okay, so first thing is wireless communication, right? So that's one application. Second is the radar. Okay, third thing is the diagnostic, right? Medical diagnostics, right? So that's one. The fourth thing is it is used for heating, for example, in microwave ovens. So whenever you have a what you call a polar molecule like H2O, water, then if you expose that water molecule to a certain microwave frequency, it is going to oscillate, right? And it is going to basically heat up whatever the content has, whatever the food or anything which has a content of water. If you put it in microwave, you can heat it. So this is used for heating applications. This is also used for some kind of surgery, right? For example, in cancers, you can treat the tumors and stuff like that. So in medical treatments also it is used. It is also can be used for imaging, right? So for example, uh, you can form these images using microwave rather than light. Like for example, in satellite applications, right? In remote sensing, you can image uh, with light, but the problem is when there is a cloudy uh, or when there is a cloud cover, then the light is not good for imaging. Okay, in remote sensing, in such times you can use microwaves for remote sensing. So imaging is one of the applications of microwave. Okay, so now once I have cleared that, okay, let's distinguish for a designer what is going to mean and what path of design you're going to take. Okay, so first thing is you should know the distinction between analog designs and then RFIC, or let's say MMIC or MIC. So RFIC is, you understood, MMIC is monolithic microwave integrated circuits, MIC is microwave integrated circuits. Monolithic means you are doing all the components on a single wafer. So that's why it's called monolithic microwave integrated circuits. If you were to use a number of microwave components and integrate them on a laminate or a board, right, or on another substrate which is like LTCC, low temperature co-fired ceramic, or LPC, liquid crystal LCP, or liquid crystal polymers, right? So these are the um, favorite carriers or laminate boards for MIC applications, right? So all that comes under MIC. Okay, then if you go up in frequency, then it can be millimeter wave ICs, and what there are new fields like instead of just antenna, you have microwave lenses and stuff like that, right? So as you go up in frequency, what happens is there are some changes, right, which you need to accommodate. Now, what is the difference between the two? Okay, in analog circuits, okay, what do I have? I have got circuits which have voltage swings and the currents are very low. So that means that the ratio voltage to current is going to be more towards infinity. So all the nodes are high impedance, all nodes are either high impedance, or all the nodes have all the branches have the current swing, but the nodes do not have voltages, very low voltages. So that means that all nodes are at low voltage or low impedance, sorry, either high impedance or low impedance, but not both, right? While in this case you have both voltage and current swings. So that means that first thing what you are going to have is a complex impedance at any node, which will be equal to the ratio of voltage, which is a complex quantity, divided by current, which is also a complex quantity, right? So that would be called impedance. So there is a concept of impedance which is medium, which is neither very high like in case of voltage mode circuits, nor very low like in the case of current mode circuits, but they are somewhere in between. The typical number we talk about is 50 ohms, and we will come to why it is 50 ohms later on. Okay, this is a best compromise between loss and power capability. So this is a best compromise between loss and power capability, right? So for example, at 33 ohms you are going to have the best power capability, but at 70, so let me see, I think it's 77 ohms or 70 ohms. 70 ohms, for example. Let's see a calculator here. Don't want to misreport something. Okay. Okay. CAL. So we have a calculator here. Okay. Let me do this before I misreport to you. I just want to check. 33 into 77. And if I was to do a square root of that, that's 50. Yeah. So it is 77 ohms. Okay. So 33 ohms is the best for power capability. And 77 ohms is best for efficiency. And the best compromise is a geometric mean of 33 and 77, which is approximately 50 ohm. So that's why all the impedances, when you are cascading, all the terminal impedances of these components are going to be 50 ohms. Okay, so this is out of the way. Second thing is, if you take there is going to be reactive powers and active powers, because V and I are finite. So you can say because they are there, you can say power, active power, P is equal to 0.5 times of real of V into conjugate of I, right? So that is going to be power. So we are dealing with impedances and power, real powers, when it comes to RFIC, MMIC or MIC, while in case of analog designs we are talking about Z either very high or very low, and the power dissipation is going to be low. So that's the difference between them. And the most, when I ask somebody, fresher, they say that if you go up in frequency and that becomes RFIC. That's not correct. Okay, uh, it is nothing to do with frequency. Frequency is just a number. What becomes a RFIC, whether you are dealing with impedances which are finite or the power which is real. So that makes it RFIC, MMIC or MIC. And if it doesn't, if there is only one which swings, then you are dealing with analog circuits. Usually analog circuits are low in frequency, but these days, because the technology has scaled down to the gate lengths which are like 5 nanometer or 7 nanometer, your analog circuits can also go into gigahertz, right? So frequency is not the distinguishing factor between analog and RFIC or MMIC circuits. So now, having said that, what category of circuits are we dealing with? We are dealing with this category of circuits. Okay, the next thing which I want to tell you is, okay, so everything is guided by, okay, a set of equations, okay, and then there are a set of quantities. So we have discussed that everything over here in propagation is E field and H field. Now let's define what is E and H. Okay, so let's define the basic terms. So you should be clear with these basic terms. Okay, first term is electric field intensity. So it's a vector quantity. Electric field intensity. Okay, now what is the measure of this electric field intensity? This unit is volt per meter. So this gives a relationship between potential and field. So in analog circuit design you would have come across this. Okay, E is equal to, okay, dou V by dou T, dou X, sorry. Okay, or rather you can say okay, so grad of V is E. So what is the grad of V? V is a scalar quantity. It's voltage. Okay, v is scalar. And if you do a grad of that, so for example in a Cartesian coordinate system, dou by dou x v I, or rather x, and then dou by dou v by dou y y, plus dou v by dou z z. Okay, so these are x, y, z are unit vectors that would be defined as grad of v, and that grad of v is minus e. Okay, okay. So this relationship you should know, this electric field intensity, and for that I have to define what is a potential, right? So for example, let's consider a charge which is capital Q. Okay, this is some Q positive charge which is measured in coulombs, and then I take a unit positive test charge which is going to have a charge on an electron 1.602 into 10 raised to minus 19 coulombs. So if I move that point from infinity, so x equal to infinity, to a point, let's say r. Okay, so if this is moved to a point r and it comes here, right? So the amount of work which you do in this, that will be called potential. Now this potential is irrespective of what path you take. So you can come with many paths, but whenever you are at a distance r, you would have done a certain work, and that will be constant irrespective of the path you have taken. So that will be called potential. So that is the definition of a potential: work done in moving a unit positive charge from infinity to a point in space where there is an electric field. Okay, so that amount of work is called potential. Now the next thing is, what is E, electric field intensity? It is the force which this charge has to overcome, so that you are doing some work, right? So this force which it sees, okay, that is called electric field intensity. So E and V have to be related in some way, because one is the work done against a force. Okay, so if the force is more, then the work done would be more, right? So why would the force be more? So for example, if Q is more, then the E is going to be more, or the work done would be more for moving to the same distance r, right? So that's why electric field intensity is related to potential. So I hope you understood what that is. Now what is this force? Force is K into Q plus divided by r square. So that would be the force. Now this force is going to be repulsive because it's a positive charge, right? Okay, so the intensity of this force basically is qualitatively linked to electric field intensity. So higher the Q, more would be the force, and more would be the E, right? So now another thing is, if I leave this charge Q at a certain point, then it is going to be repelled to infinity. So it is going to take a certain path. So for example, let's say I have a electric dipole, plus and minus. Now if I leave a positive charge here, it's going to take a certain path to arrive here. So it will be repelled from this side, but it will be attracted to the negative. So there are different paths it can take, right? Like this, and this keeps becoming bigger and bigger, right? So this is, we are talking about electrostatics. Okay, so this circle is going to become bigger and bigger and bigger, and this is going to go inside, so direction would be coming in this case. Okay, so this is what a dipole is. So if I let Q plus free, it will take a certain path to Q minus, right? Now this path trace would be called the line of flux. Okay, so when you talk about line of flux, that's there. The force which it is seeing is still called E, right? And that will be basically deciding its velocity also, right? V. Okay, so V would be, velocity V would be mu n or mu p E. It's a positive charge. So this will be mobility. So the velocity with which it will move will depend on E. Higher the E, higher the velocity it will move with, and that is related with a proportionality constant called mobility, right? So 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 E is basically related to V, but then the velocity is also related to E through a proportionality called mobility, and it's a characteristic of the medium, right? So we will come to this later on. Okay, so what I was saying was these lines of flux, right? Now these lines of flux can be very much packed together, like high density. Okay, so there is another constant, there is another this thing, uh, characteristics, which is called flux density, or rather electric flux density. Okay, and then there is something called electric field intensity, which I just explained you. So the unit of electric field intensity is V over m, velocity. This will be voltage per meter, volts per meter, right? So here electric flux density D is again a vector quantity which is related to another proportionality constant called epsilon E. Okay, now this epsilon is not just a number. This epsilon can be epsilon xx, epsilon xy, epsilon xz, epsilon yx, epsilon yy, epsilon yz, epsilon zx, epsilon zy, epsilon zz. Okay, so this is a tensor. So if this is a tensor, then this medium will cause anisotropic. Okay, so this medium will be called isotropic. Now a special form of anisotropic medium where you have all off diagonal elements to be 0. So all off diagonal elements to be 0, then that's called a polar material. Then still another variation of it is when epsilon xx is same as epsilon yy is same as epsilon zz. So we represent it just as epsilon, right? Then this would be called isotropic. So most of the mediums which we deal with in most of the discussions are isotropic material. Okay, so epsilon is permittivity, epsilon or constant, okay, it's permittivity, and the permittivity of free space is 8.854 into 10 raised to minus 12 farad per meter. Okay, now what is the unit for electric flux density? It is going to be coulomb per meter square. So let's see if this makes sense. Okay, so we have got volt per meter, right, and farad per meter. So if you were to multiply this, it will be farad into volt per meter. Okay, so okay, Q is equal to C into V, where C is a capacitance in farad, V is a voltage in, so voltage in volts. So FV basically means we are talking about charge coulomb. Okay, so that is why its unit is coulomb per meter. So you understood that? So basically the unit is coulomb per meter square. Coulomb per meter square. Okay, so this is electric flux density. Now same thing holds for magnetic field intensity H. Okay, so again magnetic field intensity H is basically the force which is experienced, right? So it's going to be magnetic field intensity. Okay, and what is its unit? Its unit is ampere per meter. Okay, and then you have magnetic flux density, the same rationale. Okay, you have magnetic flux density. How dense are the magnetic lines of flux? Flux density. Okay, and its unit is Weber per meter square. Okay, so these are the basic quantities: electric field intensity, electric flux density, magnetic field intensity, magnetic flux density. Again, B is related to constant of permeability into H. Okay, so this is a characteristics of the medium, and the medium can again be, okay, anisotropic, polar, or isotropic. So usually we deal with non-magnetic material. Then in this case, mu mu is the same as the mu of the free space, right? So what is the mu of free space? So here epsilon 0 is this. This is the permittivity of the free space, and epsilon would be equal to epsilon 0 into epsilon r. Okay, so basically then this becomes a pure number. This becomes a pure number, and this is farad per meter, which is 8.854 into 10 raised to minus 12 farad per meter. So this basically is the free space permittivity, and the overall permittivity is a number multiplied by that. Now this epsilon r is very interesting because it can also be complex. Epsilon r dash minus j epsilon r double dash. Okay, so when we talk about dielectric losses, we are talking about the imaginary part of epsilon that will be leading to dielectric losses. So we will consider this later on. Okay, similarly in this case, mu, okay, can be also a tensor, a polar, or a pure number, but it can also be a complex number. Then we are talking about magnetic losses. Okay, so now these are the basic quantities, basic relationships. Besides that, people, usually young freshers, when I ask them what is J equal to sigma E, so sigma is a pure number. So I ask them what is J equal to sigma E. They are confused. Now there is no need to get confused because this is volt per meter, right? Okay, so this is volt per meter, and this J is ampere per. Okay, so it will be okay, so it is somehow related to I into I is equal to 1 over R into A, sorry, into V. So this is volt per meter, right? Okay, and this is 1 over okay, not resistivity, rho V. Rho will be confused with that. I don't want to confuse with the rho with the volumetric charge density. What should I put here if not rho? Sigma goes with rho only, right? R into A upon L, that is resistivity. Let's say rho only. Rho is basically R into R is equal to rho into, so let me just put here, R is equal to rho into L upon A, right? Now that rho is over here. So this is Ohm's law. Whether I specify in terms of, so this is not a vector quantity. We will just take a scalar quantities here. Okay. So V is equal to IR, right? So this will be R, sorry. Okay, so this is Ohm's law, right? This is Ohm's law. So when I take J equal to sigma E, that's Ohm's law. Okay, is there a similar law for magnetic currents? Answer is no. Why? Because the magnets are dipoles, always as dipoles. So if a south pole is flowing and a north pole is flowing together, that means that the total flow is 0. Okay, so that's the reason we do not have Ohm's law for magnetic current, or we don't have magnetic current, right? Okay, so this is the basic distinction. The basic distinction is, we in case of electric, we have got isolated plus and minus charges, while in case of magnetic we are only talking about dipoles. Okay, and dipoles means that uh, there cannot be a magnetic current, right, or magnetic current density. So we cannot have Ohm's law for magnets, or magnetic field or magnetic current cannot exist, right? So there is no such relationship for magnetic. Okay, so once we are clear with these basic quantities, uh, we are where we can say what sets up a electric field E. So basically we are into a cause and effect. So we are in a cause and effect relationship. So what is the cause of, so let's say if I say curl of H, so I would have to first define a curl, right? A curl is defined this way, so this is referred to as curl. Okay, and this would be given by x, y, z. So let's say we are talking about a rectangular coordinate system, then dou by dou x, dou by dou y, dou by dou z, hx, hy, hz. So if I consider this matrix, its determinant would be curl of H. So I would have to write curl of H as dou hz by dou y minus dou hy by dou z as x, plus I would have dou hx by dou z minus dou hz by dou x times of y. Okay, and then I would have dou hy by dou x minus dou hx by dou y, okay, times of z. So this would be the definition of curl in a rectangular coordinate system. But what is actually curl? I'll explain you. Okay, this all started with a Russian guy called Osteogradsky. And Osteogradsky said that you can reduce by using this calculus, you can reduce the dimension of the problem by 1 if you consider loop or surface integrals. So that was Russian mathematician Osteogradsky. And when we went from 3 coordinate system to a 2 coordinate system, that generalization is known by Gauss, right? So basically Gauss is a generalized, it's not a, it's a specialized case of what Osteogradsky told. So Osteogradsky is the originator of all these theorems, not Gauss or your Greens or Stokes. Okay, so nobody gives any contribution to Osteogradsky, but everybody says that Gauss law is from Gauss and Stokes law or Stokes law is from Stokes. Well, it's not so. These are the specialized cases of Gradsky's law, right? So Osteogradsky is the guy. So how is it defined? Curl of H. So basically in a history you have to do some corrections. You have to give contribution to the real mathematicians, not to those scientists who stole away. Okay, so curl of H is defined as loop integral of H over a completely enclosed loop, right, divided by the area enclosed by the loop, limit area tending to 0. Okay, so this is the definition of curl. So you see, we went from a single dimension to a 2-dimension case. How? If you take delta s and go to the left hand side, you will have curl of H ds, and if you do an integral of this over surface over the surface, okay, and then this would be equal to loop integral of H dot dl. So by moving from H to curl of H or curl of H to H, we have reduced the dimension of integral from 2 to 1. Okay, so this is what is from Osteogradsky. This is known as Stokes law, but it is Osteogradsky's law. Okay, so that is the definition of curl. So how do you do this pictorially? if I consider this loop, okay, this loop has a length L. So L is the basically a vector quantity which is always tangential. And if I take H and do a dot product with this delta L or dl, and then integrate over the complete length which forms a loop, and let's say that this area is S or delta S, and the delta S is a vector quantity with a normal perpendicular to the area, right? Okay, so if I was to integrate curl of H over this entire area of S, that would be the same. And provided, so we have gone from a point form to an integral form. So this is called integral form. Okay, and curl of H, okay, is equal to limit delta S tending to 0 loop integral of over L. So let me write it clearly. So loop integral of H dot dl over a completely enclosed loop divided by delta S. So this is called the point form, and this is called the integral form. So when you go from point form to integral form, you can say that integral, which is in 2 dimensions on left hand side, becomes integral in a single dimension on right hand side, just because of the curl, right? So the curl representation, okay, makes it a 2-dimensional. Okay, so this is your definition of curl. Similarly, there is a definition for divergence of D. Okay, so for example, divergence of D. Now this is like an inner product, right? So if you have dou by dou x dou by dou y of y, and dou by dou z of z. So this is your del. Divergence of D would be inner product with dx x plus dy y plus dz z, is where this cap means unit vectors. So then this will be dou by dou x dx plus dou by dou y dy plus dou by dou z dz. So this will be divergence of D. Now what does this divergence mean? It will be defined the same way. So divergence of D would be represented as surface integral of D over a completely enclosed surface dot ds divided by the volume enclosed by this surface, limit volume tending to 0. So V is not velocity, it's volume. So this is called point form. The integral form would be volume integral of divergence of D. Okay, so here it was a surface integral. If you see, here it was surface integral, here it is a volume integral, is equal to surface integral of D over completely enclosed surface. So let us assume that there is a ball here, okay, or a completely enclosed surface. So if I have D which is perpendicularly coming out, and if I integrate D over the completely enclosed surface, that will be equal to volume integral of divergence of D dot dV. Okay, so now this is the definition of divergence in curl. Okay, and this is point form and integral form. Again, here there is a point form here and integral form here. Okay, so now let's define the cause and effect equations. So these are called Maxwell's equations. So these are nothing but cause and effect equations. So when I say curl of H, we are talking about loop of H. So what is responsible for curl of H is Js plus dou D by dou T. So now see this. This has a time variance associated with this. So this has a time variance associated with this. So if the time variance is not there, then this cannot contribute to the origin of loop of H. So if H forms a loop, then the cause for that loop is the current density Js, and the time changing flux density, electric flux density, time changing electric flux density d, right? So how would you do in terms of direction? You will do in terms of thumb, right? So basically thumb rule. So if you close all your fingers, right, as a thumb and as a fist, and the thumb projects out, right? So then if you see the direction of fingers, then the thumb is the direction of Js. Okay, so for example, if H was doing this, okay, then the thumb, so the fingers were doing like this, right? Your four fingers were doing like this, right hand thumb rule, okay, and the thumb would be pointing in this direction. So this is Js. Okay, so the reason for a loop of H is that there is a current density, okay, through that loop. Okay, then this is one reason. The other reason can be that D is changing. So D is also perpendicular here, same given by the thumb rule. D is varying with time. Okay, D is varying with the time, then the H is going to oscillate also. So one is the static case. So this is a static case. J is constant. The J is flowing constantly. So H is a constant. So H is a constant, which is a loop, a circular loop. If J is constant, Js, then Hs is constant. So this is a static case. Now, in a dynamic case, the things become function of time. Okay, so if you say dou d by dou t, so if there are electric flux which is changing in the direction perpendicular, it is changing. Okay, it is oscillating like this, right? Then H would be dancing like clockwise, anti-clockwise, clockwise, anti-clockwise, clockwise, anti-clockwise, like that. You understood? Right. So a time varying D will cause a time varying H, but it will always form a loop. Right. So this is the cause and effect situation. One is a static case, other is a dynamic case, and that causes loop of H. Similarly, okay, loop of E. Now you would say there cannot be a loop of E, okay, because loop of E should be 0, right? Why? Because this is your Kirchhoff's voltage law. Okay, so this comes from here. If you talk in terms of potential, okay, so if you take a charge Q and you move it around a loop, then the amount of work you have done is 0, because the net potential is going to become the same. So in one case you will be spending energy going closer to Q, and in that case you will be losing energy. So the net energy gained and lost would be next potential, the work done would be 0. Okay, so this is Kirchhoff's voltage law. So that means that loop of E in a static case would be 0. Okay, if it is not 0, then there has to be a magnetic current density, and this magnetic current density doesn't exist. So this is a fictitious number. That's why it is a static case of loop of E is not possible. Then minus dou B by dou T. Okay, now the dynamic case of a loop of E is possible. There can be a dancing loop of E, clockwise, anti-clockwise. Why? Because, okay, so same way, if I say E here, okay, and it is a clockwise like this, then MS has to be going in this time. So it is opposite to the thumb rule, right hand thumb rule, because there is a minus sign here. So the source of it can be a MS, which is in the negative direction. That's why minus. So there will be a loop which is a clockwise if this goes inside, like opposite to what JS was doing. MS is doing in the opposite direction. Okay, so it will be clockwise if there is a magnetic current density, and you know that magnets do not have isolated north and south pole. So if they flow also, you cannot have a current flow, magnetic current flow. So it's a fictitious number. So now this static case is not possible. What about the dynamic case? Yes. So if there is a flux density B this way, magnetic flux density B this way, and it is varying with time, then you would have a dancing loop of E, clockwise, anti-clockwise. So loop of E is possible in a dynamic case here. Okay, so this is a cause and effect situation, right? Now this cause and effect situation is also in case of divergence. Okay, divergence of D is equal to rho V, where rho V is a volumetric charge density, right? So divergence of D means that if I consider a positive charge, okay, which is a density rho V, then I would have D which will be perpendicularly coming out on this sphere. So this is a sphere, okay? So in this is a three-dimensional space, a sphere where these are coming out, okay? So if I do a surface integral of D over a completely enclosed surface and divided by the volume enclosed by a surface, it is going to be that. So I can always write this as divergence D dot ds integral over a completely enclosed surface will be equal to volume integral of rho v dv. That will be equal to the charge. So this is the integral form of equation. Okay. Did I do some mistake? Just 1 second. So this not be here, this is not correct, so this term is not there, sorry. That's the definition, right? Divided by volume enclosed, volume shifting, so volume goes to the right hand side. Yeah, so this is the correct quantity. So if I take the flux density and do a surface integral over a completely enclosed surface, then you have to do a volume integral on the right hand side of rho v, volumetric charge, that will be coming out to the total charge enclosed. Okay, now let's consider a interesting case. Let's say that this sphere, okay, has a small opening here like this. Okay, so there is a circular opening like this, right? So now let us consider a point which is the definition of D. Okay, so D is coming out perpendicularly from this surface, right? Now this volume shrinks to 0, and then there is area S. This area S also shrinks to 0, right? So now the component which I do as a curl, okay, curl of H, okay, so this will be along this loop. Curl of H will be defined as surface integral of H, okay, this will be H tangential dot dl divided by del S, limit S tending to 0, limit delta S tending to 0. Now this is a tangential component of H, okay, and I am talking about, okay, I am talking about divergence of curl of H. So now if I apply divergence, then this volume has to shrink to 0, right? So this would be, so what would happen is that one component is basically going to be perpendicular, other component is going to be tangential. So we are talking about orthogonal components now. So if you do a divergence of a curl of a vector, that's always going to be 0, because divergence is a dot product. Curl of H would be tangential, and then divergence is for the perpendicular components, so their dot product would be 0. Dot product would be 0. Yes, okay, cos theta, cos 90 is 0, correct. So dot product will be 0. So having said this, okay, let's consider curl of H. Curl of H is equal to Js plus dou D by dou T, and if I do a divergence of that, so it will be divergence of Js plus grad of, so time derivative of divergence of D by dt. So now this component is 0. This is divergence of current, and this is dou rho v by dou t from the third equation. Divergence of d is equal to rho v, right? So that means minus grad of js is equal to, or rather I would say plus this is equal to minus of dou rho v by dou t. Okay, so if there is a charge, okay, and then there is a flux out of this, okay, or if there is a current flowing out of this. So if you consider a divergence of current Js, then this charge has to shrink down, right? So if more and more current is flowing out, so Js is flowing out, then the current has to shift, has to shrink to 0, right? The charge has to shrink to 0, right? So that's why the divergence of J is minus dou rho v by dou t. Okay, so this is a continuity equation. Okay, so this is there. The last equation is divergence of B is equal to 0. This is because if I consider volume, you have north and south poles together as a dipole. North and south poles together as a, north and south poles together as a dipole. Now, if I take a unit north, it is going to be repelled, but unit south is going to attract it. So if I take the entire flux as going out versus coming in, the net is going to balance each other. So the amount of flux going out is same as the amount of flux going in, so the net is 0. So that is why divergence of B is 0, because there are no isolated north and south poles. So there is a dipole, then the divergence of B is 0. So let me summarize these equations. Okay, so this I call as Maxwell's equations. Maxwell's equations. Okay, so what are these Maxwell's equations? One is the cause of loop of H is Js for static case. For dynamic case is dou d by dou t. The next thing is cause of loops of E is going to be minus ms, which is fictitious. So static case you cannot have a loop of E, minus dou b by dou t. Okay, the third equations of divergence of D is equal to volumetric charge density rho v. Divergence of B is equal to 0. Now in the integral form it can be written as loop integral of H dot dl, okay, is equal to the surface integral of Js dot ds, okay, plus surface integral of d by dou t dot ds. Okay, and then in this case the equivalent would be here also, loop of E dot dl, which is going to be the voltage. Okay, a static case the voltage is going to be 0, but then you are considered a fictitious quantity. So static case the voltage in a loop would be 0, right? And so integral of E along a loop will be 0 because the potential is 0 along a loop. Okay, this is Kirchhoff's law. Is dou B by dou T dot ds. Okay, so this is called integral form, and then you have surface integral over a completely enclosed surface of d dot ds is equal to the volume integral of rho v dot dv. So this is a volume integral, and then surface integral of b dot ds over a completely enclosed surface is equal to volume integral of rho m dv, which is going to be equal to 0. So this is the integral form of equation, and this is the point form of Maxwell's equations. So these Maxwell's equations are important. Next thing to remember is Js equal to sigma E. That's Ohm's law. There is no magnetic equivalent of that. And the third thing to remember is, if there is a divergence of Js, then basically minus rho v by rho minus dou rho v by dou t, isn't it? That's what we derived, right? Yeah, so the charge basically just flows out, and that's what it is. And then we have a relationship between medium and the field intensity and flux density. D is equal to epsilon E and B is equal to mu h. Okay, and for free space, so epsilon can be written as epsilon r, epsilon 0, mu can be written as mu r, mu 0, and this epsilon 0 is 8.854 into 10 raised to minus 12 farad per meter, and this mu 0 is 4 pi into 10 raised to minus 7 Henry per meter. Okay, so that's there. And then epsilon r, mu r can be complex number resulting in dielectric loss or a magnetic loss. Okay, so this is a very basic of to start with. So I'm going to end this session over here, and anything which you will see is basically just the application of this, whether it is a guided wave or a free space wave, right? So I'm going to solve a case of a wave in one direction in a charge less loss free charge less medium, okay, in the next session. So I'm going to end this session over here. This was just a small brush up of electromagnetics, right? So in the next session I'm going to go into the detail, and you will start seeing the circuits coming into picture from session 3 or 4 onwards. So please bear with me to cover the basics first. And second thing is, you do not have to understand this mathematics. All you need to know is that there is something called a cause and effect situation here, or an equation here, cause and effect equation, and everything is just that. Okay, everything is just that. And if you have the intuition, you do not need to know vector calculus to do electromagnetics. Yeah, so I end here. Thanks a lot.